Hello, my name is Jonathan Takeshita, and I'm presenting Provably Secure Contact Tracing with Conditional Private Set Intersection. In the COVID-19 pandemic, contact tracing tracks personal movement and contacts to trace the spread of the disease. Privacy-preserving contact tracing is important to protect users' personal information. Some other protocols and apps that have recently been developed have various weaknesses and might leak users' locations or contacts. So without assurances of security and privacy, users may not want to enroll in contact tracing, which will decrease its effectiveness. And there is further a need for some deeper functionality beyond just basic contact tracing. This slide has a few quotes about contact tracing and privacy. The first one is about an app released by the states of North and South Dakota that had some security flaws. The second one is a more general overview, which is stating about how apps are collecting some data that they don't need. And the third one is about a specific need for more information than just basic contact tracing. The challenges we face in this research are first and foremost to provide automated contact tracing with strong and stronger privacy guarantees. We want to have minimal work on the user's part to further incentivize their participation. And we want to provide the additional functionality of filtering and computation on matches, for example, accounting for a risk score or location, again, without any additional work on the user's part. There's been some prior work on contact tracing apps that are privacy focused. So the Google Apple exposure notification, which is common on most Android and Apple phones currently on the market, uses Bluetooth messages to record contacts, and then it will have users check contacts against a released list or database of infected users' contacts. We'll talk a little bit more about this one on the next slide. The BlueTrace protocol from Singapore relies heavily on human intervention, and it does all computation in the plane, which means that users would need to trust whatever centralized server is doing this computation. The SafePaths protocol from MIT uses a GPS-based location tracking and uses private set intersection, but this protocol has some inaccuracies and privacy issues. In the Google Apple protocol, users will broadcast and collect other users' pseudo IDs throughout the day. A central server will then broadcast a database of pseudo IDs collected from infected users. Users will run the computation to match their collected pseudo IDs against the database to find a match. The problem in this protocol is that pseudo IDs from a database can easily be traced back to an infected user, which can allow several practical attacks to break privacy. So the question that we are asking in this work is, can we fix this flaw? So in modeling our system, we'll consider 4 types of parties, all of whom are honest but curious. Firstly, uninfected users. Secondly, infected users. Third, a cloud server belonging to some public health authority. And fourth, a computer equipped with Intel SGX secure hardware that belongs to the PHA and that may be co-located with the cloud server. Our desired goal for contact tracing is to preserve users' input privacy and security against other parties and against external eavesdroppers. So now I'll talk about an overview of our solution. Essentially, we view contact tracing as finding a set intersection. Doing this lets us apply protocols in private set intersection based on homomorphic encryption to this problem. Further, homomorphic encryption is capable of arbitrary computation, and interestingly, that lets us tweak the PSI circuit that's computed to allow for some additional conditions on contacts. We utilize secure hardware for things like key management and grouping user input and paring down the final result. This diagram is an overview of our solution. So first, the trusted execution environment of the PHA in our implementation, an Intel SGX, will distribute keys to users, specifically their smartphones. Throughout the day, users will encounter pseudo IDs from other users, some of which will be from infected users. Infected users, upon notification of infection, will send their broadcast IDs to the SGX, which will be pre-processed and homomorphically encrypted, and then sent to the cloud server. Similarly, users will send their encrypted sets of encountered IDs. The cloud will then compute the encrypted private set intersection of users' gathered pseudo IDs with the set of infected IDs. Finally, the results of that are sent to the trusted execution environment of the public health authority. The trusted execution environment will then decrypt the solution and return a binary result to either the public health authority or to the users, depending on the preference of the implementation. So the three tools that we use for this protocol are, first of all, homomorphic encryption, which refers to encryption schemes that allow for computations to be done on data while it's still encrypted. The second is Intel SGX, which provides secure hardware and trusted computing, with some caveats, namely drawbacks at scale. And finally, we use the protocol of private set intersection, which allows parties to securely find only the elements that they have in common. So this work from Chen et al. In 2017 uses finite field homomorphic encryption to construct a PSI protocol for honest but curious parties. The really key part here is the equation highlighted in 3b of this diagram, where it is computing this polynomial circuit that is going to be 0 whenever C sub I, or the data encrypts more precisely, is in the intersection of the user's inputs, and a random non-zero number otherwise. So what is conditional private set intersection? A conditional private set intersection protocol allows two parties to securely compute the intersections of their sets, subject to some additional condition. So essentially, the sender and receiver have their sets x and y of set elements. The receiver also has some set y prime of metadata associated with the elements of y. For output, the receiver learns x intersect y, subject to some condition p, operating on elements of y prime. The sender doesn't learn anything, and no additional information is learned by either party or any eavesdropper. So that's the definition of CPSI. Now, how do we actually construct this? Well, it's a very simple idea. First, we start with a basic PSI circuit presented by Chen et al., and we find a way to skew the result away from 0 whenever some element should not be included due to the condition. So from this equation for DI here, from Chen et al., we see immediately a very simple way to do this. Adding some non-zero value p when C sub I should be excluded will accomplish this basic goal. However, this basic idea is not quite good enough on its own. So if we suppose the plaintext space of the underlying homomorphic encryption scheme is ZT for some integer t, then we can see that there are two issues with the basic idea. The first one is that there's a small chance of a false positive, namely that simply adding p to the private set intersection result may result in an encryption of 0 by coincidence when C sub I is not in the intersection. Further, there's a chance of a privacy leak. So in the case that D sub I is equal to P, or an encryption thereof, then you can reasonably guess that the element in question for that result was in the intersection, but excluded by the predicate, with a pretty good probability. Fortunately, there is a way to fix all these problems. So let's say we let t minus k be a non-quadratic residue modulo t. Then no element of zt squared will result in t minus k modulo t. Then adding that to the square of a PSI result will only be 0 mod t, exactly when both the predicate and the PSI result are 0 mod t. So then that lets us set p equal to k when an element should be excluded from the intersection and 0 otherwise, giving us the final CPSI circuit. With these problems fixed, it's very simple to construct a CPSI protocol just by inserting the modified equation into the previous PSI protocol, which you can see there in step 3, where the PSI result is now squared and has the predicate added to it before finally being multiplied by a random number. So one question we haven't touched on yet is this predicate P, how is it actually calculated? So the approach that we took in this work was to calculate the predicate using a lookup table that is generated through polynomial interpolation. That is essentially using Lagrange interpolation to find a polynomial expression of any function from zt to zt. The degree of this polynomial is at most t minus 1, and its multiplicative depth is logarithmic in t. In practice, you can pre-compute powers of any argument x in a process called windowing, and that makes computing this function a simple dot product, which most importantly is of multiplicative depth 1. This is very important for calculating this homomorphically. So as you might have noticed, that method of calculating the predicate is directly dependent on the plaintext modulus t. We have some conflicting goals. Our first goal is to keep the plaintext modulus t for more efficient polynomial lookups. Our second goal is to keep the plaintext modulus t large. That way we can represent more set elements. So the question is, can we have both? And the full description is in our paper, but the short answer is yes, by encoding elements from z sub t to the c to z sub t, the set, multiplied by itself c times, by placing each base t digit of the element into a separate slot in the plaintext. That gives us the ability to use both a small and large plaintext space. So we covered CPSI, and our basic idea for contact tracing is to simply apply CPSI to contact tracing to allow for finding close contacts via private set intersection, and to use the predicate in CPSI to further filter for risky interactions. Essentially, we deconstruct CPSI, separating the sender into the roles of a server and a reference set holder, so that both infected and uninfected users don't have to carry out any of the heavy computation. That will be all outsourced to a server. Secure hardware is utilized for this separation. So to summarize the protocol, first, infected users will send their broadcast pseudo-IDs to the SGX of the Public Health Authority. Those will be preprocessed as a single set for windowing, which was mentioned earlier, then forwarded homomorphically encrypted to the cloud server as the set X. Meanwhile, users will be formulating their sets of inputs and metadata, that is, pseudo-IDs collected from other users, and associated metadata as Y and Y prime, and then upload those to the cloud server, encrypted, of course. The cloud server will then compute CPSI for each user, using the strategy we discussed before, and it will return the homomorphically encrypted results D to the SGX. Finally, the SGX decrypts the results and returns to each user whether or not they are infected. The SGX, depending on your preference, can either inform the PHA or simply the user of the infection result. Finally, we can do multi-hop tracing easily by simply reiterating the protocol. Now I'll talk about our proof of concept implementation of our contact tracing protocol. So we implemented our protocol in standard C++ using the BFV scheme with Microsoft Seal as our homomorphic encryption backend. Our test environment had an Intel Xeon CPU running at 3.7 GHz, 128 GB of physical memory, and running on Ubuntu 18.04. We used a partition size of 5, a plaintext modulus of 17 bits, and a polynomial modulus degree of 8192. So we used the optimizations of windowing and batching used, as well as partitioning, of course, as just mentioned. However, the dual plaintext space, modulus switching, hashing, parallelism, and other accelerations and optimizations were not used, this being only a proof of concept. We wrote standalone applications for each of the SGX processes, namely preprocessing and decryption, as well as for the user and cloud computations. We tested first on real-world data from the Project Tesserae data gathering project, and on synthetic data that we generated for testing the scalability of our protocol. So these are our results for the performance on the real-world data set from Project Tesserae. So as you can see, the basic contact tracing alone is very fast, tenths of seconds. However, the conditional parts are very slow, measured in the hundreds of seconds due to the large plaintext space. So hopefully future work will help us mitigate that large plaintext space. Similar results are seen with the synthetic data. In this test, measuring the scalability of the cloud, we see that the runtime of PSI scales linearly with the number of inputs. And the predicate calculation is again the dominating factor. As expected, we see that the runtime of the SGX program scales linearly with the number of users and has an acceptable latency for the inputs that we gave it. There are three important metrics that we consider when judging the effectiveness and efficiency of our protocol. First of all, is there a minimal computational load on the SGX? Considering the latency and scalability that was just shown, we consider this goal to be fulfilled. Second, can the computation of ordinary users be performed during overnight device charging? Again, this is easily done during overnight device charging, even when the calculation for predicates must be done. Third, is there efficient computation on the cloud side? Yes, although the calculation of the predicate, again, is highly intensive, and our future work will likely look into mitigating this. So from looking at these results, we can conclude that our proof of concept implementation can be used for a population of perhaps thousands of people. For example, a neighborhood, a college or university, or even a small city. And future optimizations can be applied for even greater scalability than what we show in our simple implementation. Before we conclude, I'd like to thank the sponsors of this work, IARPA, as well as Dr. Alex Perkins from the Department of Biological Sciences at Notre Dame, for all of their support, financial or otherwise. In this work, we presented the novel cryptographic construction of CPSI implemented using homomorphic encryption. By combining CPSI and SGX, we created a contact tracing protocol with high security and functionality. Our results show the efficacy of our protocol for smaller populations, and that it can be scaled further with future improvements. Some improvements that we have looked at or even already done include porting from Seal to the Palisade library for more features, more schemes, better customization, and the other advantages that Palisade brings. Implementing on a proper cloud platform, using a smaller plaintext space. This is pending some features for plaintext customization being added to Palisade. And an even wider exploration of parameter settings, optimizations, our dual plaintext space, different predicates, etc. Thank you for listening. The next few slides are just references.